know from the work that Louis did that lambda is equal to h over p. Let's make sure I do this in the right order. And let's see, I got that. I know that. Put my head back again. It is looking for delta F and delta T, so I have my delta T here, so now I need to figure out delta F. There we go. Frequency is equal to speed divided by the wavelength, or for a wave in general, not necessarily the speed of light. And V is equal to the momentum divided by the mass, and the wavelength is equal to h divided by p. So we get p, one-dimensional motion. So p squared over mh. I think I'm missing something here. No, that's all good. Oh, okay, no, I'm right on track. All right, so if frequency is equal to this momentum in the x direction squared divided by mh. All this is just basic mechanics here. We need to be able to get in terms of our uncertainties. So let's look at how the change in one thing affects the change in the other. So if I have y is equal to x squared, this is a little bit of calculus here. What is dy dx? Okay. Side note. If y is equal to 3x squared, 6x? Yep. All right. So we're doing the same thing here, except so df dp, since f is equal to this, m and h are both constants. M is the mass of the particle that we're talking about, and h is Planck's constant.
2p over mh.
Yep. So from that, if I multiply both sides by this, because remember that is a small quantity, but it's still a quantity, df is equal to 2px over mh times dpx. And so this is for infinitesimal changes, but if we're talking about uncertainty, we can sort of expand it a little bit. And so that the change in f is equal to 2px over mh, change in px. So I now, going back over here, I have my uncertainty here. So plugging in for f, I have 2px over mh times my delta t, which is m over px delta x, equals 1. I will hand wave that little bit. It is greater than or equal to 1. Ooh, I lost my delta t here. Px cancels out. M cancels out. So I'm left with 2 over h. Delta p, delta x is greater than or equal to 1. And so we end up with this uncertainty in the momentum times the uncertainty in the position is going to be greater than or equal to h over 2. And this is, in essence, the more we know of the position, the less we know of the momentum, and vice versa. Since momentum is related to velocity, that's the explanation of the Heisenberg code. There are a couple other dualities here. The more you know of one, the less you know of the other. Energy and time. H bar over 2, and this is the big hand wave at the end is that there's an extra 2 pi in there. And energy time, I don't have the third one written down here. Pretty sure there is a third one. That's just rehashing what I have already. Yeah, there's a third one that I'm blanking on right now. So in Star Trek, whenever they're beaming somebody from a planet to another, and technically what they would need to do is need to know the exact, if they're actually truly beaming someone to reproducing them, you need to know where every particle is, and you need to know which direction it's going in, so when you recreate it, you basically have to do the exact same thing, so that all the particles are exactly where they were before and moving in the exact same direction. Which, according to quantum physics, can't be done. Thus, in Star Trek, they have the Heisenberg compensator to figure. So at some point in the future, if they figure it out.
I feel like it'd be painful.
What was that?
I feel like it'd be painful.
Yeah, I think it would be.
I heard it's like throwing it's like throwing someone into a. I heard the idea of quantum teleportation like that is akin to throwing someone into a wood chipper and being rebuilt.
Yeah, on massive levels. Now, right now, what we're doing is the transporter technology we're doing with photons. We're not taking something and transporting it. We're actually just creating a duplicate. That's what we're doing right now. So if that's the way we go, then every time someone's transported, they're basically destroyed and a copy is made, as opposed to the actual person is remade.
I think it's best that quantum teleportation is just used for information. That's probably the safest and probably the most ethical thing to do.
Yeah, well, I don't think we quite have at the point where we can start doing particles with the rest mass. All right, so that's Heisenberg. At least that is part of Heisenberg. He did a lot more than that. All right, Schrodinger. Schrodinger comes along. I'll butcher it. Schrodinger comes up with this idea of the wave function.
That is psi, right?
That is a psi, yes. Capital psi, I think.
Yeah, I think so.
And what he's doing is that he's coming up with a function which basically describes the particle. And one of the questions early on in quantum physics was, what exactly does this mean? And what they concluded was that if I take this value and then multiply it times its conjugate, this is the probability of the particle existing at some location. So I guess of x.
So it's psi multiplied by psi sub x?
No, it's psi of x. So if the wave function is a function of position, this would be the function of position basically times itself.
Oh, I see.
And so if you add them all up, if I got the probability of the particle here is going to be such and such, here's the, I got these various places where the particle could exist. If I add up all those probabilities, what should they add up to? Yeah, because the probability of the particle existing somewhere should be 1. And so for all locations, or of course we can do this with calculus. x or whatever you're using is equal to 1. All right. So he starts with the following premises. Energy is conserved. The function is continuous. Continuous and differentiable. That's basically, this is often referred to as the function is well behaved. So first off, what does continuous mean?
It goes on forever.
No, it's not like undefined at any point. There,
Or
it has a real value at every,
it's more than that for it to be continuous. Because if I have the function that goes, not defined there, but something like that.
yeah,
Oh, well, actually, wait a second. That would be differentiable. No, I'll buy it, sorry. And then differentiable means that the slope is the same coming at it from either side, so if I'm not gonna have something like, no, continuous is that. That is, sorry. This is not continuous because I can't just basically start at one spot and end up at any other spot on the curve, in theory. Differentiable means there's sharp points. So this is not differentiable because the slope going this way and the slope going this way are not the same. This is not continuous because the function value going this way and the function going this way do not end up in the same spot. Energy is conserved. So what are my two types of energy? We're not worrying about rest energy at the moment.
Kinetic and potential?
Yep. Now, for some particular reason at this point, energy is usually represented by the letter V, which is unfortunate, but it is sort of habit. This V also stands for electric potential. All right. What's the formula for kinetic energy?
1/2 mv squared.
Formula for momentum.
Mass times velocity.
So if I square my momentum, I get m squared v squared, which I almost have right there. So if I divide by mass, I end up with mv squared, and then multiply times 1/2, I basically get that. So my momentum, my kinetic energy can also be written as p squared over 2m. Now, if we're worrying about vectors here, any vector squared is just basically, officially it's a dot product with itself. You multiply the magnitudes. So p squared, so p dot p is equal to p squared, which is just the magnitude of the momentum squared. So it works. I know that the Louis wavelength is h over p. So I have p is equal to h over the wavelength. Now, all of this, as every time I do this, I get into the same position where I'm going, they're just throwing letters up against the wall. They're manipulating stuff. And there was a book called Physics for Poets where he talks about the development of quantum mechanics, saying that the stuff they came up with was completely illogical. I mean, mathematically it flowed, but why on earth would this be true? And he said, strangely, absurd ad hoc logic that somehow managed to be true. That's the way he described quantum mechanics. And so my kinetic energy over there, I can have h squared, let's see, just where I want to do that. Actually, I'm gonna use that someplace else. Wave functions often characterized with sine functions or cosine functions, so we'll just do a cosine of kx. This k right here is the wave number. So what's the wavelength if I have cosine of x? At what point does it start to repeat itself?
2 pi.
Alright, so the wavelength is 2 pi. Cosine of 2x? At what point does it start to repeat itself?
Pi? Okay, cool, I got that right.
Cosine of 3x?
Pi over 2?
Oops,
Yeah, 2/3 pi.
2/3 pi. Basically, it repeats itself when this gets to 2 pi. You start at 0, and then when whatever's here is equal to 2 pi, that's when it starts to repeat itself. So in the first case, when x is equal to 2 pi, well, that's the wavelength. Here, when 2x equals 2 pi, in other words, when x equals pi, that's the wavelength. At 2/3, try it again. When 3x equals 2 pi, solve for x, x is equal to 2/3 pi. So similar type logic here, this small k right here, the wave number times x is equal to, when is that equal to 2 pi? Well, when x is equal to 2 pi over k. And just so I can distinguish my k's, I'm gonna put an extra loop in there, because otherwise my little k's, my big k's start to look like. So my wavelength is just equal to 2 pi over k. So P is equal to kh over 2 pi. And h over 2 pi shows up so often that that's what they make h bar. It's h bar times k. And we're gonna plug that into here. H bar k squared over 2m, which is h bar squared, k squared over 2m. Ooh, ah. Yeah, can't avoid these calculus again. So for no particular reason other than the way I'm doing it, I'm gonna let the wave function, I'm gonna do sine, I should have done sine before, but it doesn't change anything. I assume my wave function is some sine function. Again, we're talking about waves, so these things will repeat for a while. What is d psi dx? We have done it before. I know it's not necessarily something that you can necessarily do like that, but
AX sine KX.
say it again.
AX times sine of KX.
X is the unknown, so k comes out.
Yeah, okay, K times cosine of KX.
And if I do it again,
AK squared, negative AK squared times sine of KX.
we did this before when we were talking about harmonic motion. And so we had, I think I started with cosine that time, but it's the similar type pattern where you just multiply, bring this thing out. Before it was with respect to time, so it was omega times time instead of k times x, but we did this before. So I take my psi there. The real difference between these two is this k squared. So k squared times psi is equal to d squared psi over dx squared. K squared, coming back over to here. Actually, I want to do it this way. I want to multiply both sides by h bar squared over 2m. So I get k squared h bar squared over 2m times psi is equal to h bar squared over 2m d squared psi dx squared. Now the notation, again, for those less comfortable with calculus, even though you've had some, this is just a second derivative. So this right here is just my kinetic energy. It always seems so ridiculous why they did this, but